The last type of spectrum that we need to discuss is the continuous spectrum. There's actually many different ways to produce a continuous spectrum, but the one that is going to be the most important for us in this class is because of the temperature of an object. As objects heat up, they actually begin to glow. This glowing of a hot object is known as thermal or blackbody radiation. Okay, so as things begin to heat up, so when they are cold, they're going to not actually be producing any light. But as they begin to heat up, they actually start to glow. For example, if you've ever experienced an electric burner on an electric stovetop, when they are off, they're black, but as they begin to heat up, then they first start to glow red. Now, if you have them set at a low level, then they're only going to glow very faintly red. They'll start out as kind of a dull red. But if you turn it up higher, then it's going to start glowing brighter, transitioning to a bright red. And then if you really turn it up, it transitions to almost a red-orange color. Now, when a burner on an electric stove doesn't really get much hotter than that, but it does start to give the idea that we get this transition of both the amount of light and the color. So as this thing is going to continue to heat up, it'll transition from red to orange, from orange to yellow, from yellow to white, and then from white to blue. So blue is actually the hottest color. And if you remember back when we were talking about the different wavelengths and energies of light, blue light has the shortest wavelengths and highest energies. So this thermal radiation is actually following two different laws. First, each square meter of a hot object's surface emits more light at all wavelengths. In other words, as the object gets hotter, it's going to give off more light. The second thing we see happening is that as the object is getting hotter, it emits photons with higher average energy. In other words, the peak where the object is giving off the most light is going to transition to shorter wavelengths and higher energies. So in this diagram, along the bottom, we're looking at wavelengths. So notice through here, this is the visible wavelengths. We are transitioning on the right, we have red, and then the full rainbow to violet on the left. So we have long wavelength on the right and short wavelength on the left. So over here to the far left, this is going to be the ultraviolet, and over here on the right, this is going to be infrared. So again, we've got wavelength along the bottom. Up and down, we're looking at intensity, or in other words, how bright the light is at that given wavelength. So we're going to first look at this object at 3000 Kelvin. This is still too hot, don't touch it. So as you look at this curve, notice that it is giving off lots of different colors. We do have a continuous spectrum. But its peak is over here at around 1000 nanometers, which is in the infrared. Now, we do not see infrared light, but there is still visible light being given off, with a lot of that being given off over here in the red and orange. So this object is going to appear reddish to our eyes. So that was an object at 3000 Kelvin. Now looking at the object at 6000 Kelvin, first notice that at all wavelengths, it is giving off more light. The whole thing is now brighter. Also, notice that the peak has transitioned. It used to have its peak over here in the infrared. Now it's peaking over here, kind of in the blue-green region of the spectrum. Hey, again, it is going to be continuous. But because of the way our eyes work, with where it is peaking, this is going to appear yellow or yellow-white to our eyes. Okay, this is actually going to have a very similar color to our sun. Now, transitioning from something at 6000 Kelvin to something at 12,000 Kelvin, notice that at all wavelengths, it is producing more light. The whole thing is now brighter, and it is now peaking over in the ultraviolet. Now, we don't see ultraviolet, but we do have this broad part of the spectrum going through, which is part of going through the visible light. Now, most of its light is being given off over here in the blue and violet, which means that this star is going to appear blue to our eyes. In this diagram, it's the exact same thing we had before with wavelength along the bottom and then intensity up and down. The dashed curve you see through here is the thermal radiation curve for an object at 5800 Kelvin. The solid curve that's bumping up and down, that is the actual spectrum of our sun. Notice that the actual spectrum is very, very close to what we see for the continuous spectrum of an object at 5800 Kelvin. This is going to tell us the overall temperature of the sun. The surface of the sun has a temperature of around 5800 Kelvin. Now, the places that it's deviating from that, where it's bumping up higher or down lower, those are showing absorption and emission features. Okay, so these two bumps down here, that's absorption. These ones up here that are going up higher, those are emission. Okay, so the overall shape of the spectrum is going to give us the idea of the temperature of the star. And then the deviations, the dips down and the bumps up in the spectrum, are going to give us the absorption and the emission spectrum so that we can actually figure out what the star is made of. Here is our fourth clicker question. If something is glowing because it is hot, which color is the hottest? A, white, B, orange, C, yellow, or D, red? Go ahead and think about it, and we'll discuss in just a bit. All right, so if something is glowing just because it is hot, white is the hottest of what's listed here. Now, the very hottest is actually blue. One last piece when dealing with how we can learn from light. We can actually figure out the relative motion of an object, specifically whether it's coming towards or away from us. This happens because of the Doppler effect. Now, odds are you're probably actually already familiar with the Doppler effect, just not with light. You probably are familiar with it from sound. A great example of this is a car race. If you've ever seen a car race or watched the movie Cars, pay attention to what happens to the sound of the car as it zips past. So as it's coming towards, it has a higher pitch than normal, and then as it passes and goes away, it transitions to a lower pitch. You get near. And that, as it's coming towards, it's higher, and then as it goes away, it becomes lower. So what's happening in this case is as the object is coming towards you, the wavelengths are actually getting squished together. For sound, shorter wavelength means a higher pitch. Then, as it passes by, the wavelengths are then getting stretched out. They're now longer than they would be normally, and a longer wavelength means a lower pitch. So as it's coming towards, it's high-pitched, and as it's going away, it's low-pitched. We actually have the same thing happening with light. If something is coming towards us, then the wavelengths get squeezed together. And because of that, we say that it is blue-shifted, with blue having shorter wavelengths. Again, I realize violet actually has the shortest wavelengths, but for whatever reason, we say blue does. So it is blue shifted if it's coming towards us. Now, if it's going away, the wavelengths get stretched out, and the color of light with the longest wavelengths is red. So this is redshift. If we see an object is redshifted, we know it's going away. If we see that it is blue shifted, then we know it's coming towards us. So whether it's red or blue, it tells us about direction. Blue for towards, red for away. Now, the amount of shift, how big the shift is away from what it should normally be, is determined by the speed of the object. Just like with a car race, when those things are zipping around the track, they've got speeds of 100 miles per hour, maybe even more, depending on what kind of race you're watching. Compare that to somebody who's just driving down a residential road, or even better, in a school zone. You don't hear that transition, or at least not very much of it, because they're going significantly slower. So the amount of transition, if it's a large shift, then we know the object is going fast. If it's a small shift, it's going slow. If it's red shifted, it's going away. If it's blue shifted, it's coming towards. So we can actually figure out the relative motion of the object based off of its Doppler shift. All right, here is our fifth question. What can't we determine from light? A, an object's temperature, B, an object's composition, C, an object's motion, or D, we can determine all of the above from light. Go ahead and think about it, and we'll discuss in just a bit. All right, so what can't we determine from light? We can determine all of this from light. From the overall spectrum, the shape of the spectrum, we can determine the object's temperature. From the absorption and emission spectrum, we can determine the composition. Based off of the Doppler shift, whether it's red shifted or blue shifted, and how much it is red and blue shifted, we can figure out the object's motion. We can figure out all of these things. In fact, we can actually figure out even more. It's just not stuff that we've talked about yet. But we can figure out a lot just by using light.